With that, I would love to introduce our speaker today. So both halves of today's DDA community seminar will be given by Professor Kathryn Johnston. Professor Johnston is professor at Columbia University, and she is both the leader at the Flatiron Center for Computational Astrophysics Dynamics Group, as well as the chair of the Committee on Equity and Diversity for the School of Arts and Sciences at Columbia. And if you were at the DDA meeting in New York City earlier this year, you may recall she led the workshop on the Astro 2020 Decadal Survey, which led to some really good discussions and impacts that we're carrying forward in the DDA. So we are very lucky to have her join us today and share her expertise in both galactic dynamics and also in her additional work. So thank you so much, Kathryn, and please take it away.
Okay, thank you so much, Juliet and Santiago. Thanks for organizing this and pushing this initiative forward. I really appreciate it. Thanks for the lovely introduction. Actually, I have to contradict two things you said, because I've actually given up 2 of my leadership roles this year. So I'm actually neither the leader of the dynamics group nor the chair of the Committee on Equity and Diversity. I'm doing other things this year, but thank you so much. Anyway, let's just jump in. I want to give you a sort of hopefully 20-minute science talk first, and then move on to here we go. And then move on to talking about scientists and science society for the second half. And I've instructed Juliet to strictly cut us off at 30 minutes for this part of the talk to make sure we have time for the second. So really, the dynamics I'm talking about today, and it's lovely to talk to dynamicists, but we are just going to talk about an interpretation of some features that we see in the Milky Way's disks, simply with a very simple dynamical concept, and that is phase mixing. And the data we're going to talk about that we're interpreting is from the wonderful Gaia satellite. And I'm sure, as many of you know, Gaia has been up there busy since 2013, recording the sky positions of stars, 2 billion of them, over 2 billion since then. And over time, that basically gives us position and velocity. And in particular, the data set that I am going to be talking about from Gaia will be zooming into the local millions of stars best measured by Gaia to be able to map the phase space distribution function exquisitely. So just a quick overview. This is a visualization of the Gaia data release 2 in 2018. It's from the Gaia collaboration paper, but visualized by Shervin Laporte. And all you're supposed to see in this data set is to see across the galactic disk. We're looking at disk stars here. And you can see in particular, we're going to be looking at the vertical velocity here, and a beautiful visualization from Gaia that confirms some early hints is that our disk is not simply going round and round, but on average, there are ripples in this disk. And you can see on the scales here, it's going from a positive small velocity to 0 velocity, hinting into a negative velocity on scales of kiloparsecs or so. So we go from thinking about our disk as flat as our disk rippling gently up and down. And of course, we are the obvious culprit for that would be a satellite galaxy coming through. So this is a simulation from Shervin Laporte, just illustrating that idea. We have a disk, bulge, and dark matter halo dynamically interacting with the satellite. And you can see as the satellite goes through the disk, it does induce some rather magnificent up and down motion. And this is more complicated than simple warping, actual ripples through the disk as the satellite goes through. This is not the only possible, possible culprit here. I am going to just talk about this in terms of a satellite being responsible, but you can think more generally of any vertical perturbation creating this sort of response in the disk. That might be an interesting thing to talk about at the end if we have time. So what we're going to do in this talk is just remind ourselves of typical orbital properties of stars in the galactic disk and the different dimensions that they can phase mix in. And then we're going to talk about mechanisms via which that phase mixing might have been incited. And once we understand those mechanisms, we're going to go backwards and ask, well, what are the prospects for data interpretation? What can the data tell us about origins of ripples in the disk? And what can they tell us about the structure that is supporting those origins, which gets us to the mass distribution in the Milky Way and dark matter substructure and fundamentals like that. So starting with orbits, and I've got these beautiful illustrations from Wilma Trick's PhD thesis. She's just showing you, okay, most of the stars in the disk are on very nearly circular orbits. So if you look at in the phase space of X versus X, a star that's on a circular orbit in XY is going around in a circle of X versus Vx. When X is increasing, it has positive Vx. When X is decreasing, it has negative Vx. So this is a projection of a circular orbit into one dimension of phase space. If we zoom in, we can see, of course, that orbits aren't exactly circular, but they're gently oscillating in and out in radius also. And the projection in radius is also of, say, the blue orbit, again, would be a simple or close to nearly circular, well, elliptical movement in R versus VR. This is another projection in phase space. So as it's going round and round, it's gently going in and out in the galactic plane as well. And a larger eccentricity orbit is going in and out with a larger range of radii. Then we can look perpendicular to the galactic disk for these three orbits, and we can see that Wilma's chosen an exactly in-plane orbit, and one that's almost just going directly up and down, and one that's exploring all the dimensions. And again, in ZVZ, you see these different projections for different orbits. So in other words, the take home from this is when you're thinking about stars in the galactic disk, they're going round and round near circular orbits, but at the same time, they're going gently in and out from the galactic center, and they're going gently up and down. And with Gaia, we can measure these phase-space projections, R versus VR and Z versus VZ. And actually, we're going to concentrate on this last one. So the last part that we should talk about here is timescales to add up to this. This is the projection of the orbits. We're not measuring orbits. We're actually measuring instantaneous positions of stars. But how long does it take those stars to go around here? And you can think of this now, this projection as really being analogous to a projection in action. That's the area in this plane of that orbit, roughly, an angle, which is the phase along that orbit. And the frequency or time period it takes to go around that orbit, that is different. Let's look at TZ only, this orange curve. That depends on your distance from the galactic center, but it also depends on how high in the galactic disk you are oscillating up and down. So in other words, there's going to be a range of possible orbital times for the different orbits in this phase-space projection. And this is where we get into phase mixing, because in order to get phase mixing, right? Remember, phase mixing is when you start stars in a single phase, but there's a small range of orbital properties. Over time, they're going to spread out over many phases. And so this is the team that's been having fun with phase mixing over the last few years. We've got 3 relevant papers out now and a couple more coming together. The papers that I'm going to talk about today are being led by Saror Gandhi, already published, Jason Hunt, already published, and Elise Darraford, that we're currently working on. So phase mixing, just to put into a very familiar physics context, we think of a pendulum. Suppose you start pendula out all vertically initially with the same phase, but those pendula have a small range of time periods. Then what that means is over time, this is a quarter period later, a half period later, and then a full period later, these pendula are going to spread out in phase. And their projection of phase-space diagram equivalent to ZVZ is the vertical line, is when they all start off at the same phase. But as they gradually complete one full orbit in phase, they're spreading out according to the ones that are closest to the center or the ones which have largest action further from the center. That's the analogy we're talking about. Okay, so now let's look at some data. And we're going to look at data, first of all, from Gaia DR2. We're looking at data in this region of the galaxy that's closest to the sun. And this is from Teresa Antoja, the day after Gaia DR2 came out, published a beautiful paper where she projected that data into ZVZ. Our naive expectation of that projection is that if the disk is just orbiting well mixed, we should see no structure here. It should be a ball of stars. The density of the ball falls off because as we go to high distance from the galactic disk, we have fewer stars than close to the center. And the stars we see are random selections, fully phase mixed along the orbits. But of course, this is not what Teresa saw. This is the beautiful image that she saw, and she color coded this according to V5, but you can also see this in density. And you can see immediately, this is not fully phase mixed. We can actually see, almost in seeing this, that what's happening here, stars are going round and round on average in this orbit. There's been some event in the past, and it's causing a spiral. The ones in the center have gone around faster and further advanced, and the ones on the outside have gone down less fast and less advanced. So there's been phase mixing in the vertical motion here. Okay, quick pause for any urgent questions just to check that this makes sense. I'm going to count to 5. And I don't think I can see hands or anything. So Juliet, you're going to have to tell me. Okay, I'm going to move on.
Happy.
Everyone's happy. Good, I'm happy too. I'm going to move on. We've done phase mixing up and down in the disk, but the fun never stops in the Milky Way or galaxies or dynamics in general. Of course, there is also phase mixing around the galaxy. So now let's ask, these stars that Teresa has made this wonderful image for us, where did they come from? Today they're here, but these are stars on different orbits. So there could be a star that generally has a guiding center for its orbit, which is closer to the galactic center. And say that a star, an orange star that had a guiding center actually at the solar radius, that would be there at some time in the past. The red star, on the other hand, because it had a guiding center closer to the galactic center, would actually have traveled further since that time and would be further away if you looked into the past. And we could do the opposite for a star which had a guiding center further from the galactic center. Another way of looking at this is simply whether you have lower on average or higher than on average angular momentum than the orange star. And that star would have longer orbital time periods. So at the same time in the past, it would not be in the same volume as the orange star. So in other words, you have stars that are currently in phase at the volume around the sun, but in the past they were out of phase. So this is sort of anti-phase mixing as we go backwards in time. So in order to understand what's going on here, you have to understand that phase mixing is occurring up and down and round simultaneously. Of course, it's also occurring in the radial direction, but we're going to only deal with 2 dimensions in this talk for now. So the exciting thing about this, when you start thinking about interactions, is to say, okay, we've got these 7 million stars that we've got really well measured in the local volume, but actually those stars were in different places in the past. So if we're going to interpret the local volume as containing signatures of some sort of interaction that happened in the past in the form of this snail, then actually we've got more than one perspective on that interaction. So here we have, for example, if it was Sagittarius, a satellite galaxy coming down through the disk at some point in the past, the orange star, say, maybe was the closest to Sagittarius when that star came, when it came through the disk. The red star was on this lower angular momentum orbit and is slightly behind in its orbit as to where Sagittarius is. And the blue star is slightly ahead. So what this actually means is there would be no net acceleration for the yellow star if you integrate over time. In the red star, because it's encountering Sagittarius closest when it's just coming down to the disk, it would have a net downward acceleration. And in the blue star, because it's encountering Sagittarius predominantly before it encounters the disk, it would have a net upward acceleration. In other words, this, if you look at acceleration over time for the yellow star, including their motion through the disk as Sagittarius passes by, the yellow star has equal and opposite accelerations. The blue star has a predominant acceleration before the interaction, and the red star has a predominant acceleration after. So what Gandhi did was put this all together and actually color code the disk at the time today, at the time of a satellite interaction, according to how much that interaction would actually affect those stars. And you can see the systematic variations according to where those stars were in the disk at that time. And what this actually translates into, if you remember the original argument, is a systematic variation in terms of the guiding radius of the stars that we see today, or angular momentum of the stars that we see today, a systematic difference in the local volume between their interaction in the past, or their experience of whatever perturbation Sagittarius or otherwise had in the past. So in other words, this picture, stars in this local volume from different angular momentums, red, orange, and blue, were at different places in the past. And what that means is that they will have experienced this interaction differently in the past. Okay, so what that motivates us to do is actually take the data set from Gaia, that's 7 million stars in the local volume for DR2. I will show you DR3 in a minute. And locally, these stars sit sort of 7 to 9 kpc from the sun. That's in orange. But if we ask in terms of guiding radii, so you just take that angular momentum and divide by 220, and that gives you a rough guiding radius. You can actually see that these have guiding radii because of their angular momenta, which is far wider than this narrow range here. And so one of the things that Shervin Laporte actually did years ago with me was to just split the local volume into stars at lower, higher, and higher guiding radius. This is observed data. And you can see there are indeed systematic differences in the spiral you get. And I have to show you, this is the animation. Again, this is real Gaia data visualized by Shervin Laporte several years ago now, to show you how the spiral systematically changes as you see different, as you've been in different angular momenta, or equivalently, different guiding radius. So what you're doing here is you're going from, this is from the inner disk, this is the outer disk, going towards the inner disk. You can see that both the morphology and the level of winding of the spiral is changing systematically as you're going from the outer to the inner disk. Now, what I want to finish up with, just to leave you with things to think about, is the Gaia DR3 data set. This is a beautiful visualization made by Jason Hunt on the day of Gaia DR3's data release. And what I knew with Gaia DR3 was we were going to have about 5 times as many stars. So what we actually did was we split by guiding radius or angular momentum. This would be the inner galaxy and the outer galaxy. But we also split by angle. And this is actually the action angle related to the action of J phi or angular momentum. So we're splitting, in a way, we're splitting by R and phi around the disk, but we're doing it with this local sample that's within 1 kpc of the sun. And you can see this gorgeous array of spirals with differences spreading out all the way around this local volume. And if you look closer, what you really, the really fun thing we saw is, in particular, if you look at this row, you can see a 1-arm spiral. By the time you get to the innermost bin, it actually looks like a 2-arm spiral. So what we actually think we're seeing here is the local disk is going up and down. It's a bending mode on average. But in the inner galaxy, the disk has this motion. It's a breathing mode. And this has implications either for origin or for structure of the disk, or both. And the exact implications we haven't worked out yet. So what I want to end with is just blow your mind a little bit by talking about prospects. Now, this is not real data. This is a simulation. So on the left is real data. On the right is a beautiful billion particle simulation from Jason. And you have to run a billion particles to even remotely get to the sort of resolution that we find in observations. And what you can see here, this is looking across the entire galactic disk in XY. And each little pixel here contains a little visualization of the ZVZ spiral. And what you can see overall, if you just take a look at the overall picture, those ZVZ spirals have correlations across the galactic disk, meaning there are patterns in the ZVZ spirals, correlations that arise because of common origin that have subsequently been phase mixed around the disks. That is what your eye is picking up here. Let's zoom in. If you zoom in, oh, sorry, before we zoom in, I don't know if this video will work for you, but this is an animation of what I just showed you. It may be that there's too much data for this to work on Zoom, but you can actually see those spirals that I just showed you, both on the local scales and the global scales, forming in a simulation due to the interaction, in this case with a satellite galaxy. And we can zoom in locally here. This is a still to show you. Every one of these corresponds to different spirals. We actually have one-arm spirals here towards the center. If we squint, there's a hint that maybe we're getting two-arm spirals towards the edge of this disk, which is actually the opposite of what we see in the data. So the bottom line of this talk is I'm not going to tell you the interpretation. I'm just going to leave this with prospects. What we've talked about here is fundamental dynamical mechanisms. Actually, all I talked about were fundamental kinematic mechanisms of phase mixing, but they have implications for dynamics. To ask, where are these spirals coming from? Is it an individual satellite? Could it actually be an interaction between the halo and the disk? Could it be an interaction between the halo, the bar and the disk? So using the sorts of spreading across the galactic disk, we're hoping we'll be able to interpret that fundamental dynamical mechanism and learn something about the history of our galactic disk. And that is basically what I wanted to say. So I stopped the share, but we can go back to it if we need to look at images at all. I think there's time for a few questions, if Juliet lets us.
Yes, we have time for a few questions. Thank you so much for that amazing talk. If anyone has a question, go ahead and use the raise hand feature in the reactions and I'll see you. As people do that, I did want to ask, I know you just said you're not going to tell us about the fundamental dynamical mechanism. So I will ask, is the pathway to understanding what that mechanism is large N simulations like that billion particle simulation you showed us? Like, is that the pathway to get a simulation that matches the exact patterns we see from Gaia, or is there a different path to figuring out what that dynamical mechanism is?
Yeah, actually, so no, I would not advocate for that at all. I think you need the billion particle simulations as a test data set. Matching the Milky Way is not interesting. Sorry, it is interesting, but it's not interesting to fundamental dynamics. What's interesting is how we can interpret it, if that makes sense. So what we really want is to ask what the observations are telling us. And the data set is only going to be able to span a larger fraction of the disk. So what we're working on now is to really try and understand what the correlations between the local spiral and the global spiral looks like, and whether that can tell us about origin. One example, if the origin is a bar buckling up and down, you would expect a sort of symmetric two-arm pattern in the galaxy. So as you spread out, you see correlations should be in the m=2 mode. But if it was satellite going through, it would definitely be in the m=1 mode. And actually, the halo disk interaction, there's been one paper on this so far. I forget the lead author, I'm sorry, but it was within the last 2 weeks. And the halo disk interaction is another culprit. And I'm hoping that would give a more global initial interaction and a different spread of the morphologies across the galactic disk. So I think that's the way to go. And that you don't need to match it. You just need to understand how to do the interpretation. Yeah, Santiago. Oh, you're muted.
Yes, now, thank you so much for your talk. It was very nice. But I wanted to ask, because I'm a really fan of big simulations, and that simulation just blew my mind. So I wanted to ask you about the simulation, because of course, it depends on the initial conditions and what kind of model that you are using. So my question is more like, what kind of galactic model, or how do you manage to do this, and how much it differs if you change several parameters of the galaxy?
Yes, I think that intersects really well with Juliet's question, right? Because we're in this position where we need to run these obscenely large simulations to even be able to mimic the observations. And the hope of getting it right is kind of very far-fetched, although people are working on that. I think it's interesting to get it close, right? So the simulation was run by Jason Hunt using Bonsai. So it's a GPU tree code, and it's a standard satellite disk halo simulation with Sagittarius, and Sagittarius is placed following Shervin's Laporte's work of trying to let it fall in from really the virial radius to have the most longest history and evolve over time. It is a heavy model for Sagittarius. So that gives you an idea of what we're talking about. Does that answer your question enough?
Yes. Yeah, I was curious because bonsai is actually, it was in my mind, but
yes.
I just wanted to double check.
So Jason is the expert here in his work and his hours and hours. So I encourage you to get in touch. If he was on the call, I would be, maybe he is. I would be asking him to answer your question, but he is.
I am here if you want.
You want to say, Jason, you want to say anything? It's your work.
Sure. Yeah, it wasn't designed to reproduce the Milky Way. It's deliberately a warmer disk to suppress other internal structure formation, but to try and get a good laboratory for just looking at what happens after the merger. Yeah, run for about 7 gig years. Satellite falls in from virial radius, as Kathryn said. I don't know if you have specific questions, I can happily answer.
Yeah, I can. We can continue discussion after, but yeah, sure. Thank you so much. Yeah, but that definitely answered my question. So it's a generic galaxy. Okay.
Yep. Perfect. So unfortunately, I will have to cut off the science half of the Dynamics Community Seminar. Thank you so much. And you guys can talk more later. So now we're going to introduce the second half of this, because scientists don't just do science, they're also people. So I would like to introduce a second talk, also by Kathryn, this time about systemic issues in the field of astronomy. And we're going to start with a talk and then follow that with a discussion where we'll break out into breakout rooms and have discussions amongst small groups. Yeah, and Juliet, I encourage you to tell me when it's 10 minutes. Okay. Yes, I've already done. Okay, I will do that. Yes. Okay. Okay, here we go. Okay. So this work is summarized or some of this work is summarized in a paper that I wrote in 2018 during my last sabbatical. Really in response to processing some of my experiences in leadership and really having a view of academia from that position. And of course, my view is ever changing, so I have other thoughts to add at this point. It's a very compressed version, so very brief introduction and somewhat unfair, but this was leadership in science at Columbia in 2016 to 17, and I was the astronomy chair at the time. And I think the this picture speaks for itself in terms of lack of diversity among the leadership at Columbia. I would also say these are all fantastic mentors and colleagues, and that's not the criticism here. And also since then, many of these positions have actually been filled by white women, right? So there is some more diversity at this point. And here's a quote from Albert Einstein on the direction of this talk, which is really to say, this talk is presenting a toy model of me trying to think through what is the problem? Why is it so hard to tackle diversity issues? So I don't need to read this to you. We're going to, so I'm sorry, I really am talking about the majority is going to be the 59 minutes trying to define the problem. And the reason I'm spending any time doing this is in the hopes it might be useful to you. An amusing aside is actually, I got as far as writing a paper because I came across a paper by a colleague, Peter Coleman. He sits at Teachers College at Columbia. And if you look at the abstract here, it's talking about bias in discrimination and changes in these dynamics, often slow and beset with setbacks. And in this article, we present a dynamical systems model of multicultural organizational change. So when I read that abstract, I got very excited and I thought, dynamics, I'm a dynamicist, so maybe we can understand these problems after all. And also I thought it's particularly fun to present that to this audience. So my toy model, which is really translating my understanding of Peter Coleman's model, this is the bottom line. I'm introducing it quickly, so we're skipping over details here. There's no mathematics involved, by the way. This is purely conceptual. It's like you're at the start of a dynamics problem and you want to sketch out and get physical intuition, or in this case, social and societal intuition. And so what I'm doing here is I'm representing two cultures, and their dominance is the size of the area
So the cultures are different colors, and the dominance of that culture is the size of the area. And so we could say maybe in the past, science for white women, let's take the example of white women because it's easiest for me to understand that perspective. I don't want to claim a different perspective. In the past, perhaps science seemed completely dominated by a male culture and is experienced as quite exclusionary. However, it was very stable because it was one dominant culture and there wasn't a lot of different viewpoints. Currently, we're more multicultural, and there are definitely a fair fraction of women in science, less as you go to the leadership level, but still a not negligible fraction. And I would say at this point, I would describe us as rather unstable because we're in a transition, and it still can be experienced as exclusive. And actually, this is limiting in some ways. And where we want to go is where we have equal voices heard, not necessarily equal numbers, but equal voices heard, and that we are existing stably in an inclusive polyculture. That's the way I'm thinking. And just to be clear, there are many different dynamical, different groups, and I'm only characterizing with two, and I'm concentrating on this state, which I experience as a white woman in science. So my sense is, if you have this imbalance in culture and it's uncomfortable, then neither group is able to fulfill that potential, maybe because of lost opportunity for the group that has less influence. But even the group with the most influence, they're not able to take full advantage of their colleagues, and so there's unfulfilled potential. So you want to get past this stage. And the summary of the rest of the paper, I really go into how I manage conceive of how what's limiting us in terms of scientists and scientific interactions, but also systems. And the paper talks about interactions at the individual level, the unit level, and the organization level. And I represent these as positive feedback loops because they often are. They're positive, but they can have negative consequences. And in order to understand one level, you cannot ignore the other levels because your organization is made up of individuals, and your organization and unit are setting the framework for those individuals, right? So I'm going to give you an example by just looking at the individual level. And then maybe in discussion time, if that's one thing you want to do, you might want to talk about more of the system-wide level that supports those individuals. So at the individual level, there's some terminology you may be familiar with. Some I learned while I was reading Peter Coleman's article. So one word, homophily, that's what I was less familiar with, which is just simply a natural affinity of similar people. Implicit bias is unconscious effects on attitudes, judgments, and actions. Stereotype threat is this when minority status in the context of negative stereotypes can lead to discomfort and affect your performance if you're a member of that minority. So this would include demographic minorities in science, white women currently maybe in leadership roles, but others with more extreme minority status in many other levels. Imposter syndrome is doubt of accomplishments and fear of being exposed as a fraud, which I think every single person in this call will have experienced at some time. The idea is, if you look at the individual level, with this imbalance in demographics, you have to be really conscious of this sense of homophily, that it's easier perhaps to go to talk to people from similar backgrounds, even about science, and that maybe you talk about it the same way, etc. And this can lead to unconscious or implicit bias against people from other groups, maybe those in the more minority status, and lead them to feel excluded. That feeling exclusion itself can lead to a sense of being threatened and underperformance and being under constant pressure to represent your minority group and get into the majority group and be accepted and easily talked to. And that in turn, of course, that only leads to imposter syndrome, this sense that you're not good enough. And I would say imposter syndrome and stereotype threat don't make for happy people. And that can actually lead to more tensions between the dominant group in the first place, which only widens the gap culturally between the dominant group and the less dominant group. In other words, this is an exact example of a positive feedback loop that we're very familiar with in science, but unfortunately in this case can lead to very negative consequences. So the rest of the paper is really trying to take that language and try and apply it at the different levels and try and come up with examples. So at the unit level, this is sort of talking about dynamics maybe between different demographics in the department at the different levels, whether graduate student, postdoc, postbac, undergraduates, or faculty. And the organization level, of course, we're talking more about things like who gets asked to sit on which committees, how tenure packages are treated, the language in the tenure promotion guidelines, etc. Okay, so really that's all I wanted to say, because I really wanted to open this up to discussion and just give you the toy model to investigate if you're so inclined. And what I want to leave you with is this point. I have this image of interacting galaxies over here, and that's a dynamical problem. It's very complex. We talked about that today. It's an interesting challenge, right? So I think us as researchers, right, we take on complex problems all the time. We often have a very long horizon. Like, I don't think we're going to figure out the snail's problem, despite the really simple physics, for years and years to really take full advantage of it. And to do that, we're going to need to work in teams. All of this is true in terms of society as well, and scientists as well. So I urge you not to shy away from this, either because you get stymied for the first month or two, or even the first year or two, or because it seems hopeless because it's more complex. You do this every day, so you can do this. Okay, that was all I was going to say, but let me put up, just in case you find it really hard to think of what on earth to talk about, here are some simple things. Start from just asking simple reactions to this dynamical model. I would be personally interested is if you find it useful in framing your thinking at all, please email me. I'd love to hear reactions. Of course, it's always great to think about solutions. I have some ideas if we have a few minutes at the end, or rather things that I'm doing. And if you have a report on things that work, wonderful.